deadliest natural disasters in United States history. Hurricane Katrina devastated New Orleans, submerging it under a torrent of floodwater. Levees failed, and water pumping systems below sea level were flooded. The roof of the Superdome, where thousands sought shelter, was torn to shreds. And this bridge, linking the city to outside relief efforts, collapsed like a set of dominoes. How could it all happen? Now, Engineering Disasters, New Orleans on Modern Marvels. In August 2005, the close to 500,000 residents of New Orleans knew all hell was about to break loose.
I urge all citizens to put their own safety and the safety of their families first by moving to safe ground.
A monster named Hurricane Katrina was tearing across the Gulf of Mexico. The Category 5 hurricane, packing winds of nearly 175 miles per hour, was bearing down on the city and was predicted to make landfall after dark. As expected, Katrina pounded the Louisiana coastline. However, after it made landfall, it was downgraded to a Category 4 storm with winds of less than 150 miles per hour. And the eye of the hurricane veered northeast, away from the city.
At the last second, it made this little turn, and we're all so excited. It's like, no, we're not going to get the brunt of the storm. New Orleans is going to make it. We're going to make it.
Celebrations would prove to be short-lived. By missing the city, Katrina's ferocious winds, moving in a counterclockwise pattern over Lake Pontchartrain to the north, and the Gulf of Mexico to the east, sent an estimated 15-foot storm surge into the city through its backdoor drainage canal system.
Storm surge is the swell of water caused by the hurricane winds, and it raises the water level, so it's as though it's a high tide that is enormously high and just comes in fast.
Only the levees and floodwalls could protect the city from the impending catastrophe. But in a series of engineering disasters, the levees failed on a massive scale.
Once the breach occurred, there was a wall of water released, like a tsunami, that flowed into this residential area.
First, a levee floodwall broke along the Industrial Canal waterway on the city's east side. Storm surge water rushed through the breach into an area known as the 9th Ward.
I heard a loud boom, explosion, like boom. The water was so powerful that I know something was wrong, because there ain't no way in the world that much pressure of water is supposed to be coming.
Then a second flood wall on top of the 17th Street Canal levee suffered a 2-city-block-wide breach. This allowed the water of Lake Pontchartrain to run into the city. Then a third levee flood wall collapsed along the London Avenue Canal.
And you can clearly see how the walls come down, and the water just kind of pushed over it.
These levees and floodwall breaks put more than 80% of Orleans Parish underwater. Thousands of victims were left stranded.
We are dealing with one of the worst natural disasters in our nation's history.
With the city submerged, New Orleans' system of mammoth water pumps, used for more than 80 years to drain the city, was of little use.
Our biggest problem was water. Water rolled into the station, rolled across the floor. The power had to be cut to them. Water rose to this height right here. That's it. Our pumps are shut down. We're dead in the water. We're decommissioned. No more pumping.
But the flooding wasn't the only disaster Katrina visited upon New Orleans. Despite evacuations, up to 25,000 residents remained in the city. Many fled to the Louisiana Superdome, a structure built on higher ground and supposedly engineered to withstand hurricane-force winds. However, most of its roof was ripped apart during the storm.
It was quite devastating to the dome itself. It was a horrible environment to be in a space with a number of holes in the roof, water entering, no electricity, the plumbing systems beginning to back up, all as a result of these tremendous wind pressures on the roof structure itself.
Thousands were rescued from high water, many from rooftops. Getting relief to victims became extraordinarily difficult. In another engineering disaster, a main route into the city, the Interstate 10 twin-span bridge, collapsed as a result of the storm's massive water surge.
This is what the bridge looked like before Katrina. When this powerful storm came through, it just devastated the bridge. And you can see right here that there's nothing left of these 265-ton concrete segments.
The city was left with no power, scarce drinking water, dwindling food supplies, and incidents of looting.
Drop!
Up to 1,300 victims did not survive. New Orleans looked like a third world country.
It was really an apocalyptic event for the city to flood and fires to break out in the water and people to be trapped in their homes. The collapse of civilization seeming to be imminent.
Why had New Orleans been so vulnerable? A shocked nation began to look for answers.
The mystery that we're trying to uncover in terms of the engineering performance of the design is what caused the variety of failures that we saw. Was it a strong hurricane or a weak design?
An army of scientists, geologists, and engineers descended on the crippled city to unlock this mystery. One of the so-called geodetectives was Dr. Joseph Suheda, an oceanographer, geotechnical coastal engineer, and former professor at Louisiana State University.
Right after the storm hit, I investigated the causes for some of the breaches and flood wall failures that occurred. We had to do this immediately after the storm before any evidence would be erased by either repairs or some natural processes that would obscure what we were trying to look at.
Dr. Suheda reached the scene without a moment to spare.
You're Robert E. Lee, and we are...
The Army Corps of Engineers was rapidly repairing the levee and floodwall breaks to protect against further storms, which could strike during the remainder of what would turn out to be an extremely active hurricane season.
There were a lot of unknown factors in terms of the levee breaches. And so we had to look into the factors that would explain why they failed under conditions that would appear that they should not have failed under.
In fact, the engineering failures may have been over 300 years in the making. Beginning when the French arrived at the end of the 17th century. The first settlers found a swampy area they called Le Flottant, the floating land. The soil on which New Orleans was built is naturally very wet, even spongy, and consists of silt carried from the Mississippi River. The city is mostly surrounded by water. Only parts of New Orleans are a few feet above sea level. Most of it is either at or 10 feet below sea level.
The topography has been likened to a soup bowl because the front, the river end, is high, or the rim, and the middle is low, like the bottom of a bowl.
Before it was known as the Big Easy, New Orleans was named the Crescent City. the French first built on the crescent-shaped high elevation along the Mississippi River. This is where the famous French Quarter is now located. From the beginning, the French had problems with flooding from the Mississippi River. So they began to build a system of levees. A levee is an earthen dam that runs along a waterway.
The levee system goes literally to the founding of New Orleans. I would say at the very, very latest, 1720, and possibly 1718.
After the Louisiana Purchase in 1803, the United States took control of the city. As it grew, the swampland below sea level was converted into farmland. During the next 100 years, some 350 miles of levees were built to protect this new land.
Individual landowners, plantation owners, were responsible for building and maintaining the levees. So it was a very private-based, non-governmental type of action.
The dirt that comprises the base of the levees is that soft, spongy Mississippi Delta soil.
What we have here is an example of a delta soil in terms of its characteristics of having high organic content, being very, very weak, having high clay content.
In 1927, the United States Army Corps of Engineers took control of the levee system. The Corps widened many of the levees and built them higher. But as the system was strengthened, there was another problem.
New Orleans and the metropolitan area is sinking because of the geology of the soils beneath the city. The water that's in the material is being squeezed out, and so the surface has been moving down and will continue to move down for hundreds of years.
This sinking is known as subsidence. It's caused by the reclaiming of swampland. When water and mud were pumped out, the area began to fall even further below sea level. Subsidence at one time had been balanced by sedimentation. New silt, sand, and clay deposited when the Mississippi River flooded. But since the levees were constructed, the river has been controlled, and sedimentation has stopped in New Orleans.
The estimates vary for the sinking rates, but we have them as high as 1 inch a year, the typical being about a ½ an inch a year of actual sinking of the surface downward over time.
Even at a rate of a ½ inch per year, the city will subside or sink more than 4 feet in a century. For decades, geological experts warned of the peril of this sinking city and the fragile levee system that protected it.
This was a disaster waiting to happen because we knew there were hurricanes that could flood the city with the protection that we had.
Dr. Suheta was determined to find the failures that caused the levees to break. The evidence he was about to uncover would provide the first clues to how this engineering disaster could have occurred. Weeks after Katrina wreaked havoc on New Orleans, the city remained mostly underwater. The critical question: why did the levees fail? Did Katrina overwhelm the city's flood defenses, or did faulty construction cause them to burst open?
The levees and flood walls were built to what we refer to simply as a Category 3 fast-moving storm.
The National Hurricane Center classifies hurricanes according to wind speed and storm surge. The scale ranges from the least severe Category 1 hurricane, with winds of 74 to 95 miles per hour, and a storm surge of 4 to 5 feet, to the most destructive Category 5, where winds soar to more than 155 miles per hour, with a storm surge of higher than 18 feet.
Well, we started the Hurricane Protection Project back after Hurricane Betsy in 1965.
Katrina wasn't the first hurricane to devastate New Orleans. In 1965, Hurricane Betsy, a Category 4 storm with winds of 125 miles per hour, hit New Orleans dead-on and plowed through the outdated dirt levee system, flooding the 9th Ward and killing 75 people. Although Betsy caused less damage than Katrina, there was an effort to ensure that this would not happen again. The U.S. Congress gave the Army Corps of Engineers the responsibility of building concrete flood walls on top of the 7-foot-high levees to give the city more protection. They're known as eye walls. 1-inch thick steel sheet pilings were driven 20 to 25 feet underground to secure the base. Tied to them, reinforced concrete walls 6 inches thick were built on top of the dirt levees. However, the Army Corps constructed only 8-foot-high flood walls on top of the levees, for an average total of about 15 feet of protection. These could contain only a Category 3 hurricane storm surge. To fully protect the city against a Category 5 storm surge, critics warned higher flood walls should be constructed.
The Army Corps of Engineers in New Orleans was only authorized to build a Category 3 protection type system by the Congress of the United States. A Category 5 would have required different authorizations and extremely high amount more of funding.
Katrina was a Category 4 storm, with an estimated surge of more than 15 feet. Geodetective Joseph Suheda uncovered evidence suggesting one floodwall failure was caused by the action of the water overtopping it. This occurred on the east side of the city, at the Industrial Canal.
It was a condition like this where the water would come over the top of the flood wall and actually plunge down and scour at the base. And here below me, you can see what is remaining of the pit that was scoured out by the flowing water. And that scouring action would continue as long as the water kept flowing over the top of the flood wall.
Scouring occurs when floodwater pours over a wall, like a waterfall. The force of the falling water from the top of the flood wall scours or digs out the dirt along the wall's foundation, undermining it and causing the entire wall to collapse from top to bottom.
After the breach occurred, there was a wall of water released. It would be hundreds of thousands or millions of pounds of force.
The water was unbelievable. They had cars and everything washing down there. Just everything in its, we taking everything in its path, cars and everything popping up from the surface and everything. And I never seen nothing like that in my life. It was unbelievable.
Ninth Ward resident Palazzolo Simmons lived just a few blocks from the Industrial Canal levee when it failed. His home was totally destroyed.
I was right inside of here when that storm come through here, and I could not been here talking to y'all. Could have been dead. The water was so deep I had to swim from one rooftop to another rooftop. I was stranded for 3 days. 3 days with no rescue help whatsoever. I got out of this area. A guy came in with a boat, rowing a boat. He seen me, and he came pick me up.
Palazzolo Simmons was lucky. He survived. In his 9th Ward, which was hit hardest by the storm surge, miles of homes were destroyed. In another part of the city, a more insidious culprit caused the massive failures on both the London Avenue Canal and the 17th Street Canal. The very building material of the levees themselves, the soil.
As we can see here, the flood wall is in place. It's vertical, it's got a nice clean edge. We don't see any of the breaking or bending that occurred in the Industrial Canal. And that's because the mechanism of failure was different. In this case, the soils that were holding up the flood wall were saturated by the storm surge, weakened, and failed, and then slid and raised up, pushing that soil mass and the flood walls into the homes.
This is known as heaving. As Katrina's storm surge filled the canal, water pressure rose in the soft delta soil underneath the floodwalls. When the rising pressure and moving water overcame the soil's strength, it suddenly shifted, taking surrounding material and the floodwalls with it.
This is an extraordinary situation here. What we have is a piece of the original soil that was holding up the flood wall that was about 40 feet to my right along the 17th Street Canal. So this material here was actually alongside the channel at one time and got displaced and lifted upward. This fence was slightly outside the area of the flood wall. So we've seen a movement and an uplifting of the soils by about 40 feet.
This movement might have been prevented if another engineering failure had not occurred. The steel sheet pile bases, driven 20 to 25 feet underground, gave the flood walls insufficient support. A deeper sheet piling would probably have anchored the flood wall in much stronger soil.
If the soil movement takes place below the bottom of that sheet pile, then the sheet pile is really passive and doesn't protect from the soil motion. And that's what happened at the 17th Street Canal. But if the soil is strong enough, then the sheet pile actually holds up the concrete wall.
Along the London Avenue Canal, the Army Corps of Engineers is repairing the flood wall breaches with deeper steel sheet pilings. Perhaps they'll prevent a catastrophe of this kind in the future.
These are the old sheet piling underneath the flood wall. The new sheet piling we're driving are 79 feet, are these big ones right here, and these are the old ones, which are 22 feet. It's a much stronger sheet pile section than the old sheet pile.
Another repair the Army Corps has undertaken is the replacement of the old eye walls with what are known as T-walls. The flood wall is secured with a concrete base embedded underground. Attached to the base are steel sheet pilings of up to 70 feet deep.
So you have a lot of capacity in these piles where they can't be moved, so the wall can't turn as long as those piles are there.
Although the damaged levees are being rebuilt by the Army Corps, they still will only withstand a Category 3 storm surge. There are no plans to heighten the flood walls to protect against a Category 5.
The estimates, it would take many, many years, 5 to 10 years at least. Dollar estimates range in the $20+ billion range just for New Orleans area.
However, Dr. Joseph Suheta believes even if the flood walls were built higher, that wouldn't take into account the soil uncertainties, raising questions about the design of the entire levee system.
The analogy can be made that when you have very soft soils, even if you have a very strong structure on top of that, then the whole structure is going to fail. Somewhat like if you put bricks on Jell-O. The bricks can be very, very strong, but it's the strength of the Jell-O that really determines whether the bricks are going to move. One of the solutions to the problem of minimizing the threat associated with flood walls is to build floodgates at the northern end of our drainage canals, and therefore keep the storm surge from coming into the drainage canals and from threatening the flood walls.
Floodgates are enormous walls that can be raised or lowered by hydraulic systems to regulate water flow. The Army Corps is looking into the possibility of placing floodgates at canal openings.
The gate would be raised above the level of the water, so the water would gently pass beneath it. In the event a storm was approaching, the gate would be lowered so that it would block the flow of water.
Rebuilt levees, flood walls, and floodgates could constitute New Orleans' first line of defense against another hurricane catastrophe. That might help protect New Orleans' second line of defense, a system of 24 water pumping stations that flooded after Katrina and left New Orleans crippled for weeks in a polluted swampland. For more than 2 weeks after Katrina hit, New Orleans remained underwater. The city has one of the world's largest water pumping systems, capable of pumping 30 billion gallons a day. But because the levees failed, the pumps, located below sea level, became inundated with floodwater.
Water's coming in, first time ever. Electricity and water don't mix. Operators shut the station down, shut the motors off, and de-energize.
Not only were the electric pumps immobilized, pump workers literally had to swim for their lives.
At that point, I had just survival going through my mind. I wanted to live. We were all scared.
Pump station attendant Wallace Rainey had to swim in 20-foot deep floodwater to reach a stable place before being rescued.
This is where we stood as the waters was rising. It was coming in through the windows. The windows was broke. Had the water coming across the tops of the pumps. It was lapping at our feet. We were pretty scared. We didn't know we were going to make it through that day.
The men who constructed the pump stations could never have imagined the catastrophic flooding scenario that followed Katrina. For centuries, New Orleans had attempted to deal with water accumulation problems. But it wasn't until 1912 when Albert Baldwin Wood invented a successful screw pump that the city found a solution. Remarkably, many of Wood's screw pumps, over 80 years old, are still in use today. The pumps work on a very simple principle. Encased in a sealed cast iron drum, air is transferred out, creating a vacuum inside. The water is sucked in by the vacuum, and a 14-foot diameter screw, or propeller, turning at 83 RPM, propels the water out. It wasn't the actual pumps, but rather the electric synchronous motors which supply the power that were affected by the flooding. The motors are exposed to the elements and positioned in pits partially below the floor.
The water got approximately this high on this pump. And when water hit electricity, boom. Basically, you have no more operations.
It took weeks for the water to be pumped out of the stations and the motors to thoroughly dry. Then another problem caused even more delays in getting the pumps back online.
We look at this station and a lot of our other facilities as working in an actual museum, because you could look at these pumps and motors and they are extremely old. There's no manufacturer to go back to for these particular parts. So you're looking at either fabricating them yourself or going to another fabrication shop to have that done.
The city's Sewerage and Water Board is preparing its pump system for future flooding. Already there are a few prototypes in place to shield and protect the pump's electrical motors.
After the hurricane, the water was approximately here. It inundated this pump. Over at this pump, the water didn't get into the workings of the pump. It's called a sealed pump. This pump was able to be started when we got here. This is a possible solution for a situation, if we ever have it again, that's as traumatic as the storm flooding the city.
Another remedy is to elevate the entire electric system, which runs the pumps. This has already been accomplished at one station.
Some of this equipment is in the basements of some of these pumping stations. That equipment possibly needs to be higher so that if we do get a situation where we need the pumps and there's a lot of water in the city, that this equipment stays dry.
It took 21 grueling days to pump out New Orleans. But if the pumps hadn't been flooded, would the city itself have stayed above water?
If our drainage pumping station had not been damaged and the levee breach could be stopped in its early stages, it would take 12 to 20 hours possibly to pump out what ran in during that time.
Instead, standing floodwater left the city in an uninhabitable soup. Thousands sought shelter in the New Orleans Superdome. But another engineering disaster would make this shelter of last resort a living nightmare. With thousands of survivors left stranded in floodwater, the Louisiana Superdome became a shelter of last resort.
This is a football stadium. It's not a hospital. It's not a hotel. We're equipped to handle people for 4 hours, not 4 days.
Conditions deteriorated rapidly after Katrina's 145-mile-per-hour winds ripped apart the Superdome's 9-acre roof.
Hurricane-force winds began to cut, pierce, and slice this roofing system, resulting in something similar to an onion, beginning to peel back the layers. First the membrane, then the insulation, then the structural deck.
Inside the Superdome, rain pouring in from the damaged roof shorted out the main electrical system. The dome had to depend on a backup generator.
It was like living an epic disaster film. It's an unbelievable experience. So there's minimal lighting, there's no air conditioning, and it's just a matter of time before you lose water pressure. You have, 15 to 20, 25,000 people eventually in your building using the restroom with no water pressure. You can imagine what that's like. So we lost the toilets and the ability for people to use the facilities in here after a couple of days.
The Superdome was built to withstand winds stronger than Katrina's gusts. Yet the structure proved to be another New Orleans engineering disaster. Constructed in 1975, the 1.9 million square foot indoor stadium was one of the first sports domes of its kind. The stadium itself covers 13 acres. It reaches 27 stories at its peak and encloses a volume of more than 125 million cubic feet. Some 20,000 tons of steel and 150,000 cubic yards of concrete were required for its construction.
And certainly the Superdome was built to the code at that time in 1975. The building structurally is very sound. So yes, it was built to withstand hurricane-force winds.
Why then did the roof fail when subjected to Katrina's winds? The engineering disaster involved not the structure's roof itself, but rather the surface that covers the roof.
It's a rubber membrane over a 2-inch styrofoam-based material that is laid over a metal deck. And we lost one of the apex vents, one of the exhaust dampers at the very top, very apex of our roof, 270 feet above the floor.
The exhaust dampers are housed in 5-foot-high, 20-foot-long box structures, resting on the roof surface. When the hurricane winds blew one of the dampers off the roof, the resulting breach exposed the rubberized roof membrane. It began to tear. Once this occurred, the winds were able to move under the membrane seal and shred it piece by piece.
The effect on this roof was the removal of almost 70% of the membrane itself, exposing all of the structural metal deck and opening up the holes into the roof itself.
The Superdome roof would have to be rebuilt. By November 2005, the roof had been covered with a thin, temporary, hardened foam surface.
But now we're going to move to a long-term solution of a galvanized structural deck with a new foam roofing system. Hopefully we'll protect the dome better than ever. It will result in a better system, a deck that will resist the inevitable next hurricane.
However, in that desperate week after Katrina, there was another engineering disaster, impacting the thousands in the Superdome and across the city. The Interstate 10 twin-span bridge across Lake Pontchartrain collapsed because of the hurricane storm surge. Since this was one of the main routes into the city, relief supplies were difficult to deliver.
The tremendous force of nature and the awesome power that unleashed on this bridge is something that you just had to see to believe. When you're looking at these 265-ton concrete segments just being tossed around like toys.
The twin-span bridge was constructed in 1964, linking New Orleans with Interstate 10. It's a concrete structure spanning 5.4 miles of Lake Pontchartrain. The bridge consists of approximately 460 concrete segments, each weighing about 265 tons. The segments are held up by pilings that are sunk 100 feet into the lake bed, but rise less than 10 feet above the lake surface. The pilings withstood the storm surge, but because of a design flaw, some of the girders supporting the concrete segments did not.
Under this bridge span right here, the tidal surge came up and it reached probably about to the top of this girder, or right around there. It trapped air between these girders, and that caused about 1 million pounds of pressure that shoved up on this concrete segment. At about the same time, you've got probably about 750,000 pounds of pressure from a tidal surge that's hitting the side of this segment. So all of that combined to just shove this segment up and out, and it just kind of tossed it into the lake like it was a domino.
A total of 435 segments of both spans were damaged, making the bridge impassable. Because this passageway is critical to the city, it needed to be rebuilt as soon as possible. It took just 17 days to repair one of the spans.
What we had to do was cannibalize segments from one span and put them on the other span so that we could establish two-way traffic on one span. That left us with huge gaps in the remaining span. And what we did is we used bridge panels that we attached to the current structure, basically made of steel, galvanized steel. So instead of replacing those missing spans with other concrete spans, we put in these bridge panels. You can see with this new truss system and with these panels, there's really no place for any significant air pressure to build up. So it's really not going to be susceptible to the same kind of air pockets and air pressures as the concrete panels were. So that's one way that you can fix this.
By early January 2006, both sides of the twin-span bridge had been rebuilt and opened to traffic. However, these are just short-term repairs.
The long-term solution to this is to build an elevated bridge at least twice as high as the current bridge. We want to make sure that it's not susceptible to that kind of tidal surge. We believe that kind of bridge would cost about $600 million, but we believe it would be worth it to ensure that this type of tragedy never happens again.
The opening of the twin-span bridge and the repair of the Superdome are signs of New Orleans' determination to rise again. But the question remains, can the city itself, with its miles of devastation, truly be rebuilt? On Bourbon Street, the neon lights are flashing, and the booze and jazz are flowing. The Big Easy is making its best effort to come back. But the French Quarter is located on the city's highest ground and received the least amount of flood damage. Beyond it, vast areas of the city have been extensively damaged. To fund what is likely to be the largest demolition and rebuilding project in America's history, the mayor of New Orleans is asking for tens of billions of dollars in federal aid.
But we are working very feverishly with banking institutions, with financial folk, as well as federal officials to secure a line of credit that will sustain us.
But there is a looming, potentially cataclysmic crisis that may doom recovery efforts in New Orleans.
Eventually what's going to happen is that the coast of Louisiana is going to be inundated by the Gulf of Mexico.
Dr. Roy Daca, a professor of civil and environmental engineering at Louisiana State University, is now using high-powered global positioning satellites to develop true elevation points in the state.
Well, this is a GPS measuring device. This is the antenna up here. What we're using this for is to figure out exactly how high we are above sea level, but more importantly, how low we are below sea level. And what that's been able to do is that it's shown us that the sinking is occurring much faster than what people had thought before, and it's occurring in places that we didn't know it was happening.
Dr. Daka's results indicate the elevations of some areas have dropped as much as 2 feet since they were last surveyed in 1970. And the sinking continues. According to some estimates, within the next 70 years, about 15,000 square miles of land in southern Louisiana, known as the wetlands, could be underwater. The wetlands encompass a marshy region that acts as a buffer zone, slowing down hurricanes before they reach New Orleans.
We're losing, on average, a football field every hour.
The reason for the sinking is an ecological catch-22, arising from human efforts to protect against flooding from the Mississippi.
In order to stop the flooding, we leveed the rivers. We kept the river within its bank, we tamed it, but in the process, we also disrupted the natural system. Before, the river would naturally fill up areas that had subsided, and as it filled them up above sea level, higher and higher, the river then would find another course and begin to fill up other areas that had fallen below sea level.
In addition to the wetlands, Louisiana's other natural defense against hurricanes has been the Barrier Islands, which were part of the region's shoreline just a century ago. Katrina blasted right through them with Category 5 force.
After Katrina, there's not much left of the Barrier Islands, particularly the ones that have been protecting New Orleans. Much of them has been washed away. When the Barrier Islands become diminished or disappear, then there's not that impedance there to slow the action of the hurricane down.
Perhaps it was a fundamental design disaster to build the city of New Orleans on this land. Authorities are faced with an increasingly complex decision: whether to invest enormous amounts of time and money to attempt to completely protect the city with a newly designed and engineered levee system, or to simply patch and rebuild the existing system.
This is not just a New Orleans problem, but it's the entire coastal problem. And that means what we need to do is to build some sort of structure that's going to keep the water out, building a levee that might span the entire coast. This would be the biggest engineering project in the history of the Earth. This would make the pyramids look like nothing. And so what we need to do is to start new ways of thinking, start thinking about building the Great Wall of Louisiana.
But whatever the decision, the outcome for New Orleans may ultimately lie in the unpredictable hands of Mother Nature and her power to transform the Big Easy into a modern-day Atlantis.